So we're going to move into doing applications of Newton's laws now that we've learned all three laws. And the first one begins with the relatively important case of equilibrium. An object for which the net force is zero is said to be in equilibrium. The word equilibrium, which is equi plus libra, means equal balanced, coming from Latin, because for such an object, the forces are balanced and so add to zero. Also, because the first usage referred to actual scales and balances. Libra, you might know from astrology, is the sign of the balance. It's also the symbol of justice for things that are even and, balanced. Anyway, an object is stationary, then this is called static equilibrium. If the object is moving, it's dynamic equilibrium. An object in dynamic equilibrium will move at constant velocity. From a Newtonian point of view, of course, static and dynamic equilibrium are the same, though of course you might care about whether something is moving or not. We also use dynamic equilibrium because in physics there are other types of equilibrium like thermal equilibrium or electric equilibrium that are balances of other types of things. So this dynamic equilibrium will refer specifically to balance of forces. The most salient point here is, for objects in equilibrium, the acceleration is zero and so is the net force. That is, F net equals zero. But when vectors add to zero, they can be arranged to form a closed polygon. This is most useful when there are three vectors, which then form a closed triangle when the forces are in equilibrium. This asks you to draw a properly scaled free body diagram for this car, which is sitting at rest on a hill. Drawing free body diagrams, we always start with gravity because it's always there and it's embarrassing to leave out. We also know that the normal force will be holding the car out. It comes, of course, from the tires, but we're going to use the point model, so we're going to pretend it's just acting at the center, and it will be perpendicular to the incline. All right, that's the incline. There's the normal. And finally, since it's not sliding down, there must be some frictional force which points up the incline. But I haven't actually correctly scaled these, or even made any attempt to correctly scale them. What I want to go now is that to be properly scaled, all three of these should add to a closed triangle. So if I take gravitational force and I add in the normal force, I should get the frictional force. Something like this. And now these three vectors are properly scaled because they add to a correct right triangle. Notice I sort of fudged it that way. They're properly scaled because I made the triangle work out. Over here, it's possible that triangle worked out, but it doesn't look like it probably did. So these are really kind of rough and are not the correctly scaled vectors. All right. A rod is free to slide on a frictionless sheet of ice. One end of the rod is being lifted by a string. If the rod is at rest, which diagram in the figure below shows the correct angle of the string? On the next page, draw a free body diagram to justify this answer. So what we want to say is, we might even want to do the free body diagram first, really, because we want to say, well, what happens here? If we consider case A, if we did this, the string is pulling upward, counteracting gravity, but it's also pulling somewhat this way, which means that the rod would slide that way. So that's no good. Likewise, in C, the rope is pulling at least somewhat that way, and there's no balancing forces, so there's acceleration that way, so that's no good out. To stay at rest, we would have to have case B. Drawing the free body diagram is sort of interesting. We have, of course, the weight pulling down, and then we have a normal force from the floor pushing up, and then we also, of course, have the tension in the string also pushing up. This is one of those cases where I disagree with the AP way of doing things. At least it's fine for here, but it doesn't really get the essence of what's going on. And so instead we said, put the forces where they act. Well, the string acts at the end and pulls upward like that. And the normal force clearly acts over here. It's an interesting question. Where does the gravitational force act? It acts at what's called the center of mass, a concept we'll loop back on several times. Most importantly right now, the center of mass for symmetric objects is at the center of the object. So we'd have the weight doing something like this. And if I've done it right, I'm pretty close to right, the length of the weight vector should be the same downward as these two added upward. Because the net force is 0 in equilibrium, so are the components of the net force in any direction. That is, if the force is 0, then it's 0 no matter which way you look. That means that F net x equals F1x plus F2x, etc. is 0, and F net y, which is F1y plus F2y, etc., is also 0. These are three just different ways of writing the net force in x and the net force in y. Oops, missing quotes. All right, a car is pulled at constant speed across a rough road via a cable angled at 25 degrees to the horizontal. The tension in the cable is 1800 newtons. What is the force of friction acting on the car? We'll be solving this in steps over the next few slides, so don't jump to it right now. But here is our picture. We've got our car, we've got somebody pulling it, and the argument is that this is happening at constant speed. Let's draw a free body diagram for the car. We start off, of course, with its weight. We know that there's a normal. Oops. Then there's frictional forces which are resisting it. And then finally there's a tension which moves parallel, or really along the string, at the same 25 degrees. So that's our free body diagram. The key insight here is the car is in dynamic equilibrium, it's moving at constant speed, so the net force is 0 in every direction, including the x direction. The tension, of course, has a component T sub x in that x direction, right here. And that tension, that part of the tension is being opposed by friction. So if we could find Tx, we would be able to find the friction. Finding Tx is pretty easy. It's the one leg of a right triangle whose hypotenuse is 1800. So we go through our standard trig stuff and we say, well, the cosine of an angle is the adjacent side over the hypotenuse. So the thing we want, Ftx, is 1800 newtons times cosine 25, which is basically 1600 newtons. For the net force to be 0, the force of friction must be 1600 newtons the other way. All right, the weight of the car is 2150 newtons. What can be said about the normal force of the ground on the car? Is it more than 2150 newtons? Is it equal to 2150 newtons? Or is it less than 2150 newtons? We know that the normal force will be less than 2150 newtons. Why? Well, if we go back to our free body diagram, we have gravity pulling down at 2150, and we have the normal pushing up, but we also have some part of the tension, which I might call Fty. And so since the normal plus Fty have to equal 2150, then the normal has to be less than 2150. Let's find it explicitly. So we say, we take our previous thing and we say, well, we have 1800. That's pretty badly organized. (25 degrees, 1800 newtons, the thing I want. So the thing I want over 1800 newtons is the sine of 25. So the vertical part of the tension is 760 newtons. And then we have that the normal plus 760 newtons is 2150 newtons, because the normal plus the vertical part of the tension has to balance out the weight. This means that the normal force has to be 1390 newtons. As we can see, less than the weight of the car, of course.